set of notes for the year. Yay! Last topic we're going to cover this year is electrochemistry, and I figured we should probably start off with a little bit of how to balance redox reactions. And so just to refresh your memory on how you balance redox reactions, you can recognize them because you see that you have an element in a compound on one side and then the element by itself on the other, which means you know that this guy has an oxidation number of 0. So anytime you have one element changing its oxidation state, then another element has to go with it. And I just indicated nitrogen there because I know that that's already the one that does it. But before you can start balancing this equation, you have to separate it into half reactions. Before you can separate into half reactions, you have to know who was oxidized and who was reduced. And before you can do any of that, you have to know oxidation numbers. So I'm going to go through and I'm just going to label all of them with their oxidation numbers. We know that hydrogen's a +1, oxygen's a -2. So that makes this chlorine a +1. We know that this oxygen is a -2, which makes this nitrogen a +2. Chlorine's by itself, so it's a 0 charge. And this particular nitrogen, because oxygen's a -2, that means this guy adds up to a -6 overall. And since we want it to have a -1 charge, well, then that means nitrogen has to be a +5. If any of this right here just lost you, then you need to go back and review how to find oxidation numbers on the oxidation number video. So from here, I can look and say, okay, whose charge went down? Well, chlorine went from a +1 to 0. So that means chlorine was reduced. Nitrogen went from a +2 to a +5, so that means nitrogen was oxidized, which, just if you're labeling stuff, that makes chlorine the oxidizing agent and nitrogen on this side the reducing agent. Not that that in this particular case really matters, but, you know, just for your own well-being. Now, once you separate these guys into their two half reactions, the oxidation reaction and the reduction reaction, for the sake of electrolysis, not electrolysis, sorry, just electrochemistry in general, you want to write the oxidation reaction first, because whenever you draw or sketch out a voltaic cell, you'll want to keep the oxidation reaction on the left side so that you can keep track of your electron flow. So our oxidation reaction is going to be the nitrogen, so we're going to say nitrogen monoxide gives us the nitrate ion. And then our reduction reaction will just right below that. That's the HOCl, or hypochlorous acid, giving us the chlorine ion, or chlorine gas. So starting off with the nitrogens, first you balance the element itself, and this one already is balanced. And then to balance the oxygens, you add enough waters on the side that's short oxygens to keep them out. So we got 1 oxygen here, 3 here, so we need 2 more on this side, so I'm going to add 2 waters. And then you need to add hydrogens to the other side to balance out the hydrogens that you just added on the water here. So we added 4 hydrogens here, so we're going to need to add 4 hydrogen ions here. And remember, these ions, these hydrogen ions, are coming from the fact that we are working in an acidic solution. And then from there, we need to balance out our charge. So we had no charge on this side. We have a -1 and a +4 right here, so that means we need to add 3 more electrons to balance out that charge. So this one's balanced. Now we move on to the next one. Start with the element in question. So we got 2 chlorines on this side. We only have 1 on this side, so I'm going to plop a 2 right there. And then add enough waters to balance out your oxygens. So we have 2 oxygens on this side. Add 2 waters on that side to balance out these oxygens. Now you need to add hydrogens to the other side to balance out the hydrogens that you added. So we added 4 hydrogens right here. We have 2 already over here, so we only need to add 2 more. Then we need to balance out our charge. We got no charge on this side. We have that +2 right here, so we need to add 2 electrons to balance the charge out. Now, to get these 2 equations to combine, we need to make sure that our electrons are going to completely cancel each other out. So that means we're going to have to multiply this top reaction by 2, because the least common multiple of 3 and 2 is 6. And we're going to have to multiply this bottom reaction by 3. Now I'm going to switch colors here so you can see as I rewrite these. You could, multiply this through and then rewrite the entire equation, but that tends to not only take up too much time, but too much space, and you don't really have a lot of either on the AP exam. So I'm just going to rewrite this and say 4, 2, 2, this becomes an 8, and this becomes a 6. And then down here on the bottom, same thing, 6, 6, 6, 3, 6. And now we get to cancel stuff out. So I've got 4 waters on this side. I have 6 waters on this side, so that means these guys can go away, and this goes back to being a 2. And then my hydrogens, I have 8 hydrogens on this side, 6 on this side, so these guys are all gone, and this comes down to a 2. And then, of course, my electrons are going to completely cancel out, because that's the whole point of doing this little multiplying thing right here. So now I can rewrite my balanced equation. Well, I have 2 nitrogen monoxides plus 6 hypochlorous acids gives way to 2 nitrate ions plus 2 hydrogens. What do you see right here? I see a little bit of nitric acid there. Plus 3 chlorines and 2 waters. And that reaction is now balanced and everybody's happy. Alright, so getting into the actual electrolysis or electrochemistry stuff. We are going to start by talking about voltaic cells. A voltaic cell is any device that takes chemical energy and changes it into electrical energy by controlling that flow of electrons that you can have in a redox equation. Because if you take a redox reaction and you separate the half reactions into physically separated cells, then you can connect those 2 cells with a wire and actually get the electrons to flow through the wire. And as you learned in physics, anytime you have electrons flowing through a wire, you have electricity. Keep in mind that oxidation is going to take place at the anode, and I usually remember this because it's vowel and vowel, and you usually draw these on the left, and that the reduction takes place at the cathode, and again, consonant, consonant. The vowels go together, the consonants go together. And usually you draw the reduction reaction on the right. And the reason that you do this is so that when you draw these things, and I have a picture on the next slide that I'm going to show you, the electrons move from left to right, which just as human beings, it seems more natural for things to move from left to right because that's, that's how you read, that's how you count, that's how you do just about everything. And in a voltaic cell, the electrons will spontaneously move from the anode to the cathode. You don't have to put anything to it. This is a method of producing electricity. So here's a cute little picture of a voltaic cell, and on the left here I have done the oxidation reaction. Remember, oxidation involves the loss of electrons, and on the right I put the reduction reaction. So I would label this side as the anode and this side as the cathode. The other thing that I need to label on this side, I'm going to switch my colors again so you can see this a little better, is I need to label my leads, these guys right here. In this particular one, it's going to be the solid in the oxidation reaction, so this is going to be a little hunk of zinc, and this guy right here is going to be the solid in the reduction reaction, the copper solid. And in between here, in order for there to be a complete circuit, because you learned in physics too that if you don't complete your circuit, the circuit's not going to work, we have a salt bridge. And usually the salt bridge is filled with neutral, inert, not really going to participate in the reaction ions. And the most common salt to use in a salt bridge is sodium nitrate. So that's usually what you'll see. These nitrates are not coming, well, they're not entirely coming from that. I said that, I got my zinc ions from a solution of zinc nitrate and my copper ions from a solution of copper nitrate. So this salt bridge kind of connects everything, and this is our wire. The other thing that's going to want to be shown on here is the flow of electrons. And if you remember, electrons flow from anode to cathode. So I'm going to fill my little arrows in for my flow of electrons, showing that the electrons go this direction. And then the overall reaction is going to be written right down here. And we will actually talk about quantitative stuff, how much voltage are you going to get from this in just a second. But I just wanted to show you how you draw these, because you may be asked to draw one of these on the AP exam. So let's look at the calculation aspects of it. All right, EMF, electromotive force. Electromotive force is caused by the difference in the cell potentials of these two guys. This guy has a potential, a reduction potential, and this guy has a reduction potential. And it's the difference between these two that gives you the overall electromotive force, and it's that force that causes the electrons to be pushed through the wire. And just a little bit of a definition here, that 1 volt is equal to 1 joule per coulomb. Coulomb being, let me write that out because I didn't write it. C equals a coulomb. Ooh, I forgot how to spell coulomb. C-O-U-L. I can't. How do you spell coulomb? C-O-U-L-O-M-B. So a coulomb, that's what a C stands for. So 1 volt is equal to 1 joule per coulomb. And all the reduction potentials that are on that list that you get for the AP exam are based on the reduction potential of hydrogen. Hydrogen was just arbitrarily assigned a reduction potential of 0, and everybody else's reduction potentials were based on how they behaved with hydrogen. Chemistry does this a lot. They did it back with fluorine and electronegativity. They just gave fluorine an electronegativity value of 4 and assigned everybody else an electronegativity value based on how they interacted with fluorine. So this is kind of a common thing to do this. So, all of our half reactions on that list that the AP test people give us are written as reduction reactions. And it was just to simplify it. Because if you have an oxidation reaction, the value of the potential is going to be the same numerical value, but just the opposite charge. And when you're looking at two half reactions and trying to figure out, okay, which one's going to be my reduction and which one's going to be my oxidation, the one that's more positive is the one that's going to be the reduction. The one that's more negative is the one that's going to be your oxidation. I want to change colors because black is boring. And then to determine the voltage produced by any redox reaction, just simply flip the sign of the less positive guy, the oxidation guy, and add it to the more positive value, the reduction guy. That's all you got to do is simply add them up. You don't multiply them by, how many moles of anything that you have, because the reduction potentials are not, volts per mole. They're just volts. So, what is the half reaction that occurs when a silver half cell is coupled with a copper half cell? So to figure that out, first you need to write the reactions for silver and copper. We're going to pretend that we have the copper 2, or what will become the copper 2 ion. So if you look on your list, pause this and figure this out on your own, and then hit play whenever you're ready. You find that silver ion plus 1 electron is going to give us the solid silver. And for the copper half, and this has a reduction potential of positive 0.799. And then the copper is copper 2 plus 2 electrons gives us solid copper. And this one has a reduction potential of positive 0.337. So when you're looking at this and saying, okay, which one of these guys is going to be oxidized, which one's going to be reduced? Well, the one that's going to be reduced is the one that has the most positive value for E. So since silver has the highest value for E, silver is going to be our reduction reaction, which means we keep him just like he is. And copper is actually going to be our oxidation reaction, which means this gets flipped, so now it's negative 0.337. And this gets reversed to have solid copper, giving us a copper ion and the 2 electrons. So from here, what do? Well, we need to put these two guys together. This reaction deals with 2 electrons. This one only deals with 1. So we need to take this top reaction and multiply it by 2. We do not multiply this value of E. And again, the reason that we don't have to multiply the value of E by 2 is because the units on E are just volts. If it was volts per mole, then yes, we would have to multiply it by this 2 right here, but it's not. It's just volts. So I'm going to put these two equations together, and I end up with 2 silver ions plus 1 solid copper gives me a copper ion plus 2, I just did parentheses, 2 solid silvers. And to calculate the potential of this particular reaction, the voltage of this reaction, I take 0.799 and subtract 0.337, and I end up with the potential of this particular cell would be positive 0.462. And this reaction is just going to happen. If you put a copper solution on the one side and the silver solution on the other, copper anode, silver anode, this reaction would just go. You wouldn't have to do anything to it. It would produce 0.462 volts of electricity. I don't know however often, but ever so often. And maybe it just produces that many volts of electricity. And it's spontaneous. So a positive E value is correlated with a spontaneous process. Well, we talked about spontaneous stuff before in relation to free energy. And I did not change my fonts. These are all supposed to be deltas. I apologize. It's kind of annoying to change one letter font, so I just changed it on here. Okay. If you remember, back in the last section, we learned that a negative value of delta G means we have a spontaneous reaction. Well, you just now learned that a positive E value for your redox reaction means that you have a spontaneous reaction. And so they're kind of opposite in sign. And this is the formula that relates delta G and E, where delta G is the standard free energy in kilojoules per mole. N is the number of moles of electron that are transferred. F is Faraday's constant, which is this special little number right here. It is written on all of your formula charts that you have for the free response section of the AP exam. So you don't have to memorize this number, but it's a good number just to have, like, to be able to recognize it and know what to do with it. And I put the units here as coulombs per moles of electron, but it's probably a little more useful to know it as joules per volts times mole electron. Notice delta G is in kilojoules, Faraday's constant is in joules, so that will need to be dealt with. And then E is the cell potential in volts. This one has the units of moles because it's moles, or mole E. So you notice mole E gets canceled out here, volts gets canceled out here, we're left in joules for delta G, which means we need to go bloop, 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 and scooch it over so that we're in kilojoules. So I'm going to do one example, and then we'll go ahead and cut this video off, and I'll do a part 2 in just a second. So, sketch this voltaic cell, assuming aluminum, zinc half cells suitably connected at 298 Kelvin standard conditions, and that both aqueous solutions are 1 molar concentration. So, sketch the cell. So, I'm going to draw my beakers, and I'm going to put my electrodes in here. You do not have to be a great artist to be able to do this. I'm a horrible artist and I can still do this. Connect them with your wire. Draw. Oh, whoa, yeah, the liquid's not going out of the beaker. Go like that. And then put your salt bridge. And so we need to figure out which one's going to be because this side's going to be our anode, which means it gets the oxidation reaction. And this one is the cathode, which means it's going to be our reduction reaction. So we got to figure out who's going to be reduced and who's going to be oxidized. So the aluminum half reaction is Al3 plus 3 electrons gives us solid aluminum. And zinc is going to be zinc 2 plus 2 electrons gives us solid zinc. So looking at our list that we get for the AP exam, we see that the aluminum has a reduction potential of negative 1.66, and the zinc has a reduction potential of negative 0.762. So, which one of these guys is more positive? Well, the zinc is the more positive one, so that's going to be our reduction reaction, and the aluminum is going to be our oxidation. So I'm going to write the aluminum half reaction over here at the anode. Al3 plus 3 electrons gives me solid aluminum. And at the cathode reaction, I'm going to flip this. Wait, whoops. I was supposed to flip the oxidation, my bad. So it becomes solid aluminum, turns into aluminum ion, plus 3 electrons. And in the cathode, you write just as it is. So the zinc ion plus the 2 electrons gives us solid zinc. And then, so we got what node they occur at, so this is going to be solid aluminum this is going to be solid zinc, and in here we'll have our zinc ions and our aluminum ions. This will be our salt bridge, so I'll just put some sodiums in there and some nitrates in there. Put some nitrates in here, nitrates in here, and there you go. And then draw your flow of electrons. So the overall reaction, putting these two guys together, you notice this one's 2 electrons, this one's 3. So we're going to have to take this guy and multiply him by 2. This guy multiply him by 3. So we end up with 2 solid aluminums plus 3 zinc ions. Gives me 2 aluminum ions and 3 solid zincs. Then calculate E for the voltaic cell. Well, since we flipped this guy, that means we flipped this sign. So you end up with 1.66 plus a negative 0.762. And that works out to 909, well, it's 898, something like that. But sig fig wise, it works out to 0.90 E of this cell equals positive 0.90. Next question, calculate the free energy. Well, delta G is equal to negative number of electrons transferred. Well, since the least common multiple of 3 and 2 is 6, we transferred 6 moles of electrons. And then multiply that by F, 96,485. Keep in mind that's in joules per volt mole E, so I'm going to go ahead and say 96.485 kilojoules per volt mole E. That way I don't have to do any kind of conversion later. And then my E that I just calculated is 0.9 volts. My units over there. And you plug this into your nifty little calculator, and it works out to a negative about 520 kilojoules. And does this number make sense? Yeah, it makes sense, because E was positive, which means this is spontaneous, and delta G is negative when the reaction is spontaneous, so there you go. And right here, is the reaction spontaneous? Well, yes it is, because E is positive and delta G is negative. Now they want us to calculate K for this particular reaction. And if you remember, in the last topic we had the formula of delta G equals negative RT natural log of K. And keep in mind, this R, we're using 8.314 joules per mole Kelvin. And since this is in kilojoules, I'm going to go ahead and convert my G value here to 520,000. And it's negative 520,000 equals negative, so I can actually get rid of these negatives since there's a negative on both sides. R, 8.314 times my temperature up in the question right here is 298. And it's the log of K, or natural log of K, that I will be solving for in just a second. So you isolate all this stuff, get log of K by itself, and you see that the natural log of K works out to 210. And when you do the inverse natural log, or take E and raise it to the 210th power, you get that K is equal to the most astronomical number I've ever seen, 1.6 times 10 to the 91st power. This number is huge. In fact, it's the biggest number I've ever written. And what this means is that this reaction goes so far over to the product side that there's virtually no reactants left at all. Everything is in products. And so if we were to allow this reaction to go to completion, this sad little piece of aluminum right here would just be gone, because it would all be eaten up by this reaction right here. So huge value for K here. That is all I'm going to put on this particular part. I will do on the second part how to do EMFs at non-standard conditions, and a little talk about electrolysis and electroplating.